Hello everyone and welcome to the next virtual seminar. This is Aparna Deshmukh. I'm Technical Director with Next and I will be your moderator for today's session. We are eager to learn all about our virtual seminar that is on advancement in polymer utilization in 3D printing construction industry. So a PDF of this presentation can be found in the handout box. You can use the PDF to follow the presentation and take notes. You may also use the question box to ask questions, and a speaker will address the questions after the end of each presentation. For continuing education credit, attendance for the entire duration for the entire for today's live virtual seminar will earn you a certificate of completion for 5.5 PDH. Your certificate will be available in ACI University under the certificates tab within 2 days. For those who cannot join us live, the on demand recording will be made available about a week after the live presentation. ACI is an approved education provider for the American Institute of Architects and the International Code Council, and this webinar has been approved for 5.5 PDH. This is a disclaimer. Please take note of our disclaimer on the screen for all the presentations in today's virtual seminar. So without any delay, I would like to just show you the schedule for today's virtual seminar. We are going to start at 10. It's already 10. And we will have a break from 12:30 to 1 p.m. And we will resume at 1 p.m. Till 4 p.m. So please stay with us till 4 p.m. So starting with our first presentation, uh, titled Advanced Functional Materials for Sustainable Water Treatment, Synergy of Polymers and Additive Manufacturing. And for this presentation, I would be happy to introduce our speaker Dr. Voon Long Wong. So Dr. Voon Long Wong received his PhD in engineering from the University of Nottingham, UK in 2015. He is currently an assistant professor in chemical engineering at Xiamen University, Malaysia campus, and he is a chartered engineer with IChemE UK and the Engineering Council UK. He is also a professional engineer with the Board of Engineers Malaysia and a fellow of the Higher Education Academy. Dr. Wong serves on editorial boards of several journals and is active in international committees. His research focuses on microfluids, additive manufacturing, environmental science, and functional material. So let's welcome him and listen to his presentation.
All right. Good morning, everyone. It's night times from Malaysia here, but it's happy to see you all here attending this talk. And thanks for having me here. And I'd like to especially thanks to Dr. Aparna who giving me the opportunities. Although my area is not fully working in the constructions industry, but some things that related to the 3D printings and may give you some ideas or some of the sharings my research in this additive manufacturing for the wastewater treatment. So I believe that most of you know that the additive manufacturing is a quite important element in these latest revolutions due to the green fabrications and its high design flexibility. And there are seven families of the AM technology, as I believe that you know about the material jettings, the wet photopolymerization, binder jetting, and material extrusion, etc. So these seven categories of the commercially available AM technology mostly follows the ISOs and ASMTM standard. So there are a wide range of the materials can be utilized in the AM fabrications. They are categorized into three main categories, which are the polymers, ceramics, and also the metals. Among these materials, polymer-based AM techniques has possesses the highest level of maturity and demands. As can see from the statistic data, they has expected about 19.7% of the compound annual growth rate within the forecasted periods of 2020 to 2024, with the impressive USD 24 billions in using this polymer-based AM technology. And besides that, I have checked a little bit on the construction itself. Based on the internet's data and online resources, found out that actually 3D printing in construction actually have three main contributors from the US, Europe, and Asia, with the expected 91.5% of the CAGR with the constructions markets that is expected to increase to 680 million USD by 2030. So 3D printings in constructions, they have a most common material they use, like standard concrete, concrete, plastic polymers, metals, or local natural materials or composite. All right, so basically, would like to give you some of the ideas. What are the typical materials used for the particular 3D printing techniques? I have compiled a series of the methods based on the seven families. That what are the common material selection and what currently they are used this 3D printing methods for what type of applications here. So for example, for the first family is the powder bed fusion. It's a powder-based technique. There are four different methods here: SLS, MJF, SLM, and EBM. So 3D printing method for these powder bed fusions normally is joins the powder material by point by point using an energy or heat sources such as like laser beam. And there are quite common material selections, mostly polymers, metal, ceramics, and composites. And I realized that actually powder bed fusions has some of the research using these methods for the constructions uh, application. But PBF seems like not widely adopted in the mainstream construction. It's mostly the researchers are focused on how they're enhancing the strength of the cement for the metal casting using this powder-based fusion. So based on the data that I have is the methods for the construction are still in the nascent stages, which is the development stages. So there's a lot more of ongoing research are addressing the scalability, materials developments, and also the integration with the existing constructions practice. While the wastewater applications, SLS and SLM, they commonly use it for the membrane filtrations and also spacer for the water treatments. And other fields that have using the powder bed fusion, such as like aerospace, dental, mechanicals, and the electronics. Apart from the powder-based bed fusion, they have binder jettings and directed energy deposition. Also have some existing research that working for the constructions industry, and but they have not using much on the polymers because the binder jettings and DED they mostly use on the metal, ceramics, and the composites. And binder jettings can be considered as the second popular 3D printing technology after the extrusion. So for the construction, so emerge as a quite versatile manufacturing method here. And the binder jettings also has been used for the porous filter to print the porous filter and use it for the oil and gas industry for the water application. But there no any available data has been reflected the DED has been used for the wastewater treatment. For other fields are quite common as mentioned previously, like mechanical or dental or electronics are quite common using these two types of the printing techniques. Besides that, we have a material jettings. So material jettings are liquid based, and I highlighted here is considered as a resin based technique. It's quite common for using for the wastewater treatments. They also have uses like researching in for building or manufacturing the spacer and membrane, and other fields is like dentals and biomedical. While the material extrusion, this is one of the earliest stage or earliest techniques has been adopted for the constructions industry. There are two types. One is the FDM, one is the IW. Normally is the solid base or liquid base differences. And then they have used the polymers as well as part of their common material selection. While for wastewater treatments as well, material extrusion is not just only common for construction, it's also quite common for the wastewater application and other fields as repeated as previously mentioned. And besides that, one of these sheet laminations, the sheet laminations, they have no available data basically for the construction, and no available data that has been used for the water and wastewater application. So they have some solid base methods using polymer, which is the LOM, and there's a limited material selections for UOM and STL, only metals or paper. So from here, we can see that there are some of the research gap that has not been done for water treatments and construction, and something that's maybe can be used as a alternative way for the application itself. And last but not least is the wet photopolymerizations. So wet photopolymerizations are not common in construction, and I don't have any available data really talking about the VP methods in the construction, but we have a lot of other fields that has been used these two methods, these few methods, which is the wastewater treatments and the biomedicals and pharmaceuticals. So mostly they are also considered as a resin-based technique because they are all in a liquid base, and they have most of the methods are available for the material, which is polymer, ceramics, and composites. All right, so generally giving you the ideas about the polymers additive manufacturing, it possesses the high maturity level of maturity and demand. So why it's so attractive here is because of the benefits and advantages from the lightweight properties, the rapid prototyping, and its functional structure, because it can be easily to enabling the creations of the intricate prototypes, and also essential for the design, testing, and innovation. Besides that, they have a very good flexibility in design and processing, especially they are having a low melting points or liquid states that are easy to process as well. And apart from that, they also consume low energy, and because of the limits of the waste that produce, at the same time it also reduce the carbon footprint due to the lesser waste. So it's quite aligned with the sustainability goals here. So if you're looking at the waters and wastewater treatment and construction industry, because now I'm more towards the wastewater treatment itself, and we can see that additive manufacturing are quite well known and show a very high promises to produce a very high performance, low cost, and sustainable design in the area of environmental science and also construction. And there's quite a number of papers has been published using the additive manufacturing for both of these application. However, if we narrow down the polymers AM itself, and actually the numbers is dropping. So we can see that the wastewater treatments, the number of paper publications is not really a lot. It's quite small number, but we can see that there is a growing trend for the researchers to explore and see how they can increase the utilizations of this 3D printing in the wastewater treatments for tackling the issue of the water resources scarcity. And while construction industries, we can see the number of paper publications for the polymers AM started from 2016 until now is quite a large number of the paper have been published in this area. And I believe that when the technology can become more mature and become more cost effective, it's likely that even more countries will adopt the polymer 3D printings to revolutionize their constructions, industrial, or even those the wastewater treatment here. All right, so now we more focusing about the water research. So I have three common polymers normally they have been using in this AM. They are thermoplastic, thermoset plastic, and photopolymer. So I also giving this example that normally what are the example of thermoplastic polymer that have been used with the brackets that you can see that like SLS and FDM are quite like a established methods, 3D printing methods using the thermoplastic. And thermoset plastic, they have the 3D printings normally use the thermoset plastic are PBF, the material jackings, the extrusion, even the photopolymerization. While the photopolymers, the quite common 3D printing methods will be the SLA, DLP, and MJ. So the abbreviation you can find back to my notes, and you can roughly know what are the full names of the 3D printing methods. So basically, if look at the figure 8.6, you can see that most of our existing research for the water, for the 3D printing in water research, they covers the membrane technology, adsorptions, advanced oxidation process, and bioreactors application. So these are the quite common polymers AM fabrications. So I will talk about a little bit more about what are the current printing parts that has been used for the membranes, absorptions, and also other application. So in this table A2 is reflects those polymeric material consideration. What are the current polymer has been used for the polymeric materials in the AM technology for the water research. So basically we have 7 common families of AM, but for water research, the common ones will be only powder bed fusions, material jettings, material extrusion, and wet photopolymerization. We're working on this existing polymers material consideration. All right, so let's give you a general idea about the water and wastewater treatments and why we want to use 3D printings in this water treatments. So if you're looking at this wastewater treatment stages as taking as one of the common practice. So wastewater treatment typically involve with the 3 different stages like a primary treatment where the solid particles are removed through the sedimentation, while the secondary treatments are using the biological processes to break down all the organic matter. And last but not least, the tertiary stages involving the chemical or advanced filtration techniques to further purify the water and remove the remaining contaminants. So most of the existing research for the 3D printing in wastewater treatment are mostly targeted on the tertiary stages. Um, Even though our research currently is also focuses on the tertiary stages, especially how we can use the 3D printings to modify the filters or the filters physical modification, and how it targets the further discolorations of for the textile wastewater treatments or further polishing step to reduce the BOD and COD, which is the oxygens, chemical oxygen demand and biological oxygen demand. So we were taking the 3D printing as a advancement stage for the um, tertiary treatment stages. So you will see a lot of mostly they are talking about the filtration, membranes. Most of these cases are always putting on the tertiary stages. Yeah. All right, let's start with the first, which is the membranes technology. So membrane technology is one of the most common applications that has been widely used the 3D printings in fabricating the membrane and the spacer. We have about 31% of the 3D printing has been used for the ultrafiltration, and 19% of them are used for the reverse osmosis. If you're looking at the left side of the presentation slide, you can see a different type of structure and porosity of the different design for the membrane or spacer by using a 3D printing. So based on the AM fabrications part, you can see that we have several of the membranes and spacer has been fabricated by using different type of the AM techniques, and also different polymeric material has been used for this membrane fabrication. And then there are certain some of the research has been done for the pollutants removal. You can see a difference. The pollutants has been used by chewing this membrane that fabricated using the 3D printing. So why it's so important when they want to replace the 3D printing here for as compared to the conventional? So current results for the is very challenging is because of the conventional fabrications method. So as I know from the conventional fabrication methods, they have 2 common method, which is the thermally induced phase separation Another one was a vapor-induced separation. These two methods are consume a lot of amounts of the solvent, and which will generate a large amounts of waste stream. So in these cases, we are trying to give a green fabrications to treat our treatments, that at the same time we do not want to generate so much waste. So because we want to treat the water, at the same time we do not want to generate the waste. So that's why those conventional methods has restricted the diversity of the membrane design for the different separations module. So therefore, certain of the existing published research from all the researcher or scientists, they have used this AM technology for the membrane fabrication, which allow a flexible design and freedom in the 3D dimension, giving them benefit in a single step process, solvent-free, cost-effective, and greater energy efficiency. All right, besides that, we have advanced oxidation process and also bioreactor application. These two they are not as much widely used, the 3D printings in targeting the wastewater treatments. I have filled some of the data here, which is the AM fabrications. They have using it for the advanced oxidation process, which is using the TiO2, the titanium oxide, and the photocatalysis to remove the contaminants of the emerging constants, such as the methyl blue dye or oflicecins. While the others was the major highlighted by the researcher was the bioreactor applications such as the biocarrier, capsule, and the growth plate. And mostly they are targeted to remove on the organic matters such as the phosphorus, nitrogen, pathogens, ammonia, and even the pharmaceuticals pollutants. So they have used it to design, and they compare the 3D printer with the commercial one. And although the performance are not as good as the commercial one, but it's something like an alternative while playing with the different design, as you can see from the diagram here. Besides that, we have this another quite common applications which is the absorptive separation process, adsorption. They also have widely used the 3D printer to such as the FDM, DLP, DIW, which is the three main families of the AM, to fabricate the different parts of adsorbent, targeting on removers, certain applications here. And then there is quite a numbers of them are using for the applications in the wastewater treatments. And from the diagram, and you can see also the different designs and different type of the MOF, which is the metal organics frameworks, has been used here as well for the adsorption process. All right. So now I'm more focusing on how I really working on the water research. What is my research currently doing on it? So the last slide, the previous slide, I have talked about more to the adsorption itself. So mostly I target adsorption, and then I'm using a different type of materials for targeting the textile wastewater treatment, because textile wastewater treatment is one of the major issues in Malaysia. So we are seeing that how we can target on this textile wastewater by using this green fabrication. So we use the MSLA as a technique, and it's a wet photopolymerization method. We use a different materials such as HDT resin and eco UV clear resin, to be coated by the photocatalyst itself. So if you see on a diagram, we have a before coating and after coatings. We can see that there's a clear coating, clear photoreactor HDT resin with the smooth surface, while we coat with the GCN, which is a carbon nitride thermoset coating. And why we want to coat the photocatalyst, and why we not just use the photocatalyst itself? Because if you want to use the photocatalyst is a powder form. When you have a powder form, you need to have an extra post-processing step, which is the centrifugation, and it will giving more energy consumption step. So we're trying to avoid the centrifugations, and this coatings photocatalyst has really well coated on the photoreactor itself, and it will avoid the leaching parts, it will avoid the centrifugations. It's really helping a lot of time effectiveness. So therefore, and also besides that, the photocatalyst that we coated actually is a super hydrophilicity, which is giving a very high water adhesive to the water and giving a good surface area when we working on the photocatalysis and also the absorption process. We managed to retain 98.5% efficiency after a 5 constituent cycle, even though after 10 consecutive cycles, it still retain a high numbers of 90% of efficiency here. Apart from the photoreactor, we also play around with different type of the how I would say is a monolith itself. We have a different type of the monolith design like diamonds, IWP, and gyroid, and we also use it because different design here. You will give you a different surface specific surface area. So we found out that doesn't mean that high surface specific surface area will give you a better shapes or better removal rate. And based on whatever we see is that the gyroids, which is the gyroids, which is number 3, although the specific area is about only 18.84 centimeter cube square, but the performance giving it is much more better as compared to the others design. So there is something quite interesting is that when we see this result, is maybe because of the something that we have not optimized is the water permeability. So we assume that maybe the water permeability for gyro shapes is much better than the diamonds and IWP, even though the surface area is not high. All right, so besides that, we also have one of the research has working on the 3D printed PECDA monolith with rubber sling grafted chitosan. If you can compare here with the previous slides that I have for the other research, we can see that different materials actually is used for different type of the active material. So previously what we've seen here is HD resin as a support, photocatalysis as the active material for targeting the water treatment. While this one, PECDA was the support as printing as a support material, and the chitosan was the active material. So GPTMS and FPTMS actually are the cross-linking agent to bind the chitosans to the PECDA, because PECDA is well binded to the chitosan itself. So chitosan is something that polymers that is quite well established methods material, but they have a very latest research has working chitosans on coating on the PECDA itself. So we have coated the chitosans on the PECDA, and we have done this also use it for the textile wastewater treatments, taking the sample from the industry, and we found that this chitosans with the 3D printers had given a very good reductions of the BOD, which is 62.4% of the reductions, while the CO2 reductions for the real wastewater treatments, which is only 2%. In these cases, we can see that 22.4% good numbers that can meet the discharge standard B based on our environmental quality at 19.74, but the CO2 reduction is quite low and for the real wastewater samples, and 3.9% for the synthetic water sample. So in these cases, we only may base to, as I mentioned previously, is just we only can take it as a further polishing step, but we cannot use it for the real as the real treatments. Only can be put it as a further polishing step. But however, this is something that in the future we could have a better ideas and how we can improve. So besides that, we have this also playing around with the structural topology of the different 3D printing PECDA monolith. This research actually is a research that relates to the previous slide, and then so we also use the MSLA to print the materials itself, and we use a different type of the shades to given here. And then we found that the standard cubic, which is I previously showed in the previous slide, this is a standard cubic structure, and it's actually is quite giving a better performance compared to the fissures, gyroids, and the kagome. And besides that, the permeability giving a highest permeability for the center qubit with the removal of the MO die as 90.4%. So this gives a very good mechanical stability for practical application. And we found that there's no any significant weight loss before and after absorption. So this is something that can be think of how we can commercialize or upscale into for the industrial application. Actually, we are currently working on this project is like to how we can upscale into fluidized big reactors, and we're putting the fluidized big column into the for all of this onolith we put into a pack back design to see how we can work it on the continuous process, because currently whatever we are using the existing research are basically are in the batch mode. So these are the features publications that I have published in the different different journal here, and you may have a take a look, and when you have a time you can read through the journal here. So last but not least is the challenges and the future prospect. I believe that AMS has provided a great alternative for fabrications of this biodegradable polymer material, a high reusability of the material based on what we have seen and what my research has been observed, and it's actually offer a quite remarkable advantages over the traditional manufacturing method. However, it's still a early stage, and most of the reported works and research are still at the laboratory scale. And we actually have a very lack of extensive assessments to justify economic feasibility. So we really need to see how we can justify the economic feasibility, especially the production cost. And we will have to know that using the polymer material still become as a new paradigm in the manufacturing, and it really offers a wide promise and the convincing innovation in the water treatment, and even though for other application. So that's all my presentations for today, and I hope that my ideas has been shared to you guys, and maybe you have some new ideas or innovation in the future. All right, that's all for now. Thank you, and I'm open for any questions.
Thank you so much, Dr. Wong, for your presentation. It was very informative. Um, so we have one question. And for the audience, if you have more questions, please write them on the question box. Um, so is there any practical implication of this additive manufactured water treatment you have done?
The practicals, just now we have mentioned, one of the slide is we did not like I would say our technology readiness level is up to level 4 or 5, and we have did with the testing with the textile industrial water. We get a sample from the industry, but we do not like actuals putting this AM technology to the industrial real practicals. I mean the operation, yes. But in the lab skills, we did taking the sample from the site, and then we test the COD and BOD level. But for practically for the commercial side, which is the upscale part, there is a long way to go, which is we are currently working on the pilot skill. So we will hope to see that these pilot skills can be really work into the industrial one day. So this is something that we are currently working on it.
Okay, great. Thank you. We have our next question. It is about how this additive water treatment product will affect the current technology.
It's I would say the you means the 3D printings, how it will affect the current technology. It really depends on the applications itself, because it's like not, I would say not all the 3D printers can be well used in the technology, especially some of the parts that we still need to really understand the material properties itself, because we need to know how's the properties able, especially when you can't just build the polymers, like for example you build a polymers base buildings in a country that has a have earthquakes, all this testing, we must really need to understand how we can really understand material properties, whether it's suitable for certain country or whether they're suitable for certain applications. So material properties, the assessments, the regulatory compliance, all these safety issues are still need to be considered before we utilize it.
Yeah, before the practical implication, right?
Yes.
Yeah. Great. Thank you so much. Thank you for your informative and interesting presentation.